Hello everyone. So today we are going to present the paper A Virtual Switch Platform for Host SDN in the Public Cloud. This is published by Daniel Firestone, and the main motivation behind this paper is that it identifies the challenges in existing software-defined networking. So what is SDN? So basically SDN is an approach to network management that uses software to control and direct traffic on one network. So basically, the existing HDNs have many issues, which include scalability issues, which can be defined that they are unable to handle large volume of traffic and tenants. And also they have policy enforcement limitations and also tenant isolations. So basically, when we consider existing SDN solutions, uh, we can say that there are many challenges, as I mentioned, in scalability and tenant isolation. For instance, in public clouds like Azure, the inability to handle large-scale multi-tenant environments obviously limits the service quality, and this is the main motivation why VFP has been proposed. So the impact, most important part of this paper is that it addresses these challenges, which are practical implications. These practical implications ensure secure and reliable service for millions of users. Also, it contributes theoretically by advancing the SDN architectures for better scalability and flexibility. Uh, if you see cloud platforms try to host millions of tenants requiring high scalable SDN solutions and at a very cheaper rate. So it also gives us like helps us improving many economic impacts, which reduces the overhead and operational cost for cloud providers. So the solutions would directly benefit the cloud service providers like Azure or AWS and of course the customers. Uh, so the author in this paper has introduced VFP, which is Virtual Filtering Platform, and it is Azure's SDN data plane. So he had set 2 to 3 goals which are to be achieved by this proposal. The first one being to provide a model that allows multiple simultaneous independent network controllers to program network applications, minimizing cross-control dependencies. This is nothing but to provide network controllers uh, without any conflicts. And also, uh, he wanted to provide a MAT programmable model capable of using connections as a base primitive. The third goal being is the main part where uh, it was proposed to create a scalable and flexible data plane that uses a stateful flows as a core primitive. Okay, now let's talk about the existing solutions and the shortcomings. So the current solution is Open vSwitch and OpenFlow. So again, uh, these have similar kind of issues and limitations. One being the performance bottlenecks. These solutions have high latency and also high overhead, CPU overhead. Again, they have scalability constraints, like they cannot be effectively scaled uh, if the traffic or the demands keep on increasing. And these have very rigid designs, like they lack the flexibility to adapt to dynamic tenant policies. All these shortcomings are to be improved, and the proposal which this paper is about meeting these shortcomings. So the importance of problem is that it pushes the SDN innovation to next level, and also it directly impacts the public cloud scalability. And the use cases are Azure distributed firewalls and load balancing. So the main idea of VFP, the virtual filtering platform, is a programmable virtual switch designed for Azure, and it has key features which include stateful policies that operates based on the connections, not just packets. And also they include multi-controller support. Multi-controller support tries to enable independent network controllers. We also can see that it provides efficient caching, which reduces the latency, which is really important, and also improves the throughput. So the core challenges like scalability, performance, and tenant isolation are being addressed, and the process of how this has been implemented will be taken over by Srikar.
Uh, Good morning, everyone, and I'm going to explain about the implementation design of this particular paper. So as we can see, VFP operates on Hyper-V extensible switch right here. And VFP implements MAT, which is also called as match action tables as layers, which matches packets IP address and takes appropriate actions. VFP usually assumes that switch with multiple ports are connected with NIC, or we can precisely say virtual NICs, because uh, yeah, and VFP filters the traffic from virtual NIC to switch, and from switch to VNIC, which is also called as inbound and outbound traffic. So the inbound traffic, which is also called as egress traffic, travels from switch to virtual machine, and outbound traffic, which is also called as ingress traffic, travels from uh, travels from switch to NIC. So NICs are usually used to give MAC address to each individual packets, so that so that it can take an appropriate IP address and match appropriate virtual machines while uh, during an outbound traffic. So so that virtual machines can receive each virtual machines belonging to that particular MAC address can receive that particular packet they're bound to receive. So coming to our uh, so So ports are basic unit. Uh, अरे आप रहा. So ports are usually basic units of filters, and layers here have basic flow tables that have a match action table policy, and groups are entities which are related to group of rules. Like each group has a particular set of group of rules which we can filter based on what they usually match on. So, and rules are basically entries. So, each rule is basically an individual entry on in the match action table. And uh, and coming to uh, and coming to the layers, uh, ports policies are usually divided into layers. Layers are basically match action table themselves. So uh, controllers can create how many like can create many match action, as many layers as they want, and they can order it in any manner. For example, they can have VDIP NAT after VNet, or VNet after VDIP NAT. So they can order as they please. So each layer has their own inbound and outbound rules. So packets go through each layer one by one, and controller can specify as I said, controller can specify the order. As you can see, there is an inbound direction from VIP to direct IP, which NAT translates NAT translate which from VIP to DIP, and from for the outbound direction we have uh, For outbound direction, NAT usually translates DIP address to a VIP address. So we can say VIP is a virtual IP address given by the virtual machine, and DIP is the direct IP address of that particular virtual machine. So we can divide that
Which
particular
is
space. We
pos
can say that particular
begin.
space has a virtual address space, which the space
Coursera.
which above that particular
Once
boundary
starting
is
the
called
Pada.
as DIP address space, and space below that particular boundary is called VIP address space. And we have
Yeah, over to
and VL2 is
Sakshi side.
implemented by
We will
VNet.
continue with the
VL2 is
next part.
implemented by VNet, which creates a
Engine.
customer address which creates a boundary between customer address and physical address. So the space above it is called as customer address space, and space below it is called as physical address space. So we can while in an inbound direction, the packets are usually decapsulated to that particular customer address, and then and in an outbound direction, the packets are usually encapsulated into a particular packets. So, and on top of NAT layer, we have an ACL layer, which basically acts like in a firewall. So it matches the DIP addresses, and does 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 the particular action, but according to that particular DIP. And on top of ACL, we have metering rail, which usually calculates the inbound traffic and outbound traffic. Next. So as we can see, VFP achieves scalability through multi-controller support, policy offloading, optimized packet processing, and real-world testing. So as we can say that multi-controller support uh, can give an independent controllers program different layers without conflicts. So there wouldn't be any conflicts, and independent controllers can control their particular layers, and can have different each controller can have a different inbound and outbound rules. So policy offloading, it offloads flow policies to programmable NICs to handle high traffic volumes. So what it does is it takes the policies from the controllers and gives it to NICs, so that it can the virtual NICs can handle so that NICs can handle the high traffic volumes, and I mean, it can divide the traffic volumes between NICs uh, NICs and controller, so that controller can send the packets uh, more easily, and with high speed. Optimized packet processing uses metadata pipelines for efficient packet handling. So it usually uses one particular IP address per se. It uses VIP addresses, virtual IP addresses, which is easy to filter out which packet is going to which controller, or which packet is going to which particular virtual machine, so that it can divide VIP into DIP, and give it to each particular virtual machine. So real world testing. Proven deployment over 1 million Azure hosts demonstrated scalability and reliability. Key metrics: scalability, flows per host. So it uh, there are host can have a lot of flows. They can have they can give a, I mean, host can send a lot of packets and receive a lot of packets simultaneously. Performance, latency, and throughput. So since we have multiple controllers, so we can assign each controller to each host, or so that and they are independent to each other. So the controllers are independent to each other. So the packets would easily go through the layers, and we can receive the packets in an optimized way. Reliability, and kind of uh, it is kind of reliable since it has a lot of security layers such as ACL, which acts like a firewall for each of the packets, so that we can check if the particular address is valid or not. Main results. Uh, some of the key findings are VFP achieves high scalability, supporting millions of machines and tenants. Demonstrate, uh, Demonstrates significant performance improvements with low latency and high throughput. Ensures robust tenant isolation and flexible policy. Next.
Takeaways from this paper are laser design, scalability, serviceability. Laser design, critical for modular and scalable policy enforcement. Serviceability, frequent updates with minimal downtime, improvement reliability. Scalability, efficient catching and flow management mechanism ensure performance. VFP sets a benchmark for designing SDN solutions for large scale cloud environments. Why this problem matters? Scalability, flexibility, security. Scalability, supporting millions of tenants in public cloud environments. Flexibility, enabling dynamic policy changes without service disruption. Security, ensuring robust isolation for tenant specific configurations. Comparison of existing solutions. VFP compared to existing solutions like Open vSwitch, stateful design. VFP uses stateful policies for NAT and ACLs, unlike OFC's stateless models. Scalability. VFP's un- unfined flow tables handle large larger traffic volumes efficiently. Flexibility. VFP allows dynamic policy changes, unlike the rigid designs of OVS. Gaps in current solutions. Resource intensive, high, o- high overhead in CPU, memory usage, complexity in tenants isolation policies, limited scalability beyond certain flow per host. Scalability and performance benefits. VFP introduces innovations, efficient use of CPU resources, sca- scales horizontally to support growing cloud demands, stateful flow management, tracks connection state to optimize pack handling, reduce redundancy and latency in tenant policies. Challenges and overcoming them. Key challenges addressed by VFB: maintaining tenant isolation in dynamic environment, achieving near zero overhead in high traffic situations, integration into Azure operates as a core part of the Azure SDN stack, provide seamless experience for Azure users with enhanced network policies. Demonstration of results. Evaluation covers scenarios, high traffic, tenant specific routing, matrix, flow, flow throughput, CPU efficiency, consistency of results. Multiple test cases demonstrate reliability VPN consistently outperform alternatives in real-world deployments. Implications for future SDN paves the way for more scalable public cloud solution, demonstrate potential for hypervisor hypervisor based innovations. Noble contributions. The noble contributions of this paper includes stateful MAT model, independent controls, undefined flow tables, efficient offloads. These innovations significantly advance SDN capabilities in public clouds. Overall lessons. Key lessons from this paper. Importance of layering and modular design in SDN. Scalability through stateful and efficient catching mechanisms. Prioritizing serviceability and frequent updates without downtime. Did the author achieve what they sent out to do? Yes, the author successfully achieved their goals. They set they set out to create a programmable VFP of Microsoft Azure that would support multiple independent network controllers, allow controllers to define custom policies, provide high performance through caching, support hardware offloading, enable frequent updates without service interruption. The paper demonstrates how they achieved each of these goals thorough through performance ensure performance measurement showing improvements, real world deployment data for running on one me- uh, 1M host for 4 plus years. Documentation of lessons learned and operational experience. Is the paper well organized and presented? Yes, the paper is well organized, well structured, clear progression for motive to implementation of to results, effective use of figures and diagrams to illustrate concepts, good balance of high level architecture and technical details, thorough comparison with existing solutions, strong focus on practical experience and lessons learned. What did we learn from this paper? Key Key learnings included technical insights, operational insights, architectural insights, insights, how to design a programmable virtual switch that supports multiple independent controllers, method for implementing stateful network policy efficiently, approaches for hardware offloads of network policies. Operational insights. The importance of serviceability and rebootless updates in production environments. How to handle state management during updates and VM migration. The value of keeping the forwarding plain simple. The challenges of working with commercial NIC hardware of DNS. Architectural insights. Benefits of separating the wire protocol from the data plane. Why layering is critical for multiple controller scenarios. How to design for both programmability and performance. The advantages of modeling network functions has actions rather than interference. The paper provides valuable real world experience for operating a large scale cloud network, making it practically useful for both research and practitioner in the field. Thank you.
So to add up to this, VFP has a great real-world relevance, and that can be proved by the fact that the scalability is over 1 million hosts, which proves its robustness and also has a practical applicability. VFP also provides many features like monitoring and serviceability, which adds up to the goals the author has set. And at the end, I would like to conclude that VFP is a trailblazing solution that bridges the gap between scalability and programmability in SDN systems. It serves as a foundation for future interactions in cloud scaling networking. Thank you.